Dear Professor Julia Greer, dear participants, dear colleagues and friends, a very warm hello everyone and welcome. Welcome to the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize for national and international audiences, relying on the unifying feature of science for humanity that surpasses geographical boundaries, languages, races, and cultures, providing us with the power and wonder of shared ideas and understanding. We also organize these seminars to minimize the negative impacts of COVID-19 situation in the world on scientific thought and its creation. With this in mind, it is my pleasure to let you know that this evening we have another wonderful episode of our interdisciplinary seminar series. And I have a distinct pleasure and honor to introduce you our very special speaker, Professor Julia Grier from California Institute of Technology. Professor Julia Grier has kindly agreed to join us for this seminar, and she is going to give a great talk entitled Materials by Design, Three-Dimensional Nano-Architecture Metamaterials. Professor Julia Grier is a Rubin and Dana Mettler Professor of Material Science, Mechanics, and Medical Engineering, and the Director of the Kavli Institute at Caltech. Grier's research focuses on creating and characterizing classes of materials with multi-scale and microstructural hierarchy with combined three-dimensional architectures with nanoscale induced material properties. Her specific topics include applications of three-dimensional nano and micro-architected materials in chemical and biological devices, ultra-lightweight energy storage systems, filters for purification, and chemically assisted separation, damage-tolerant fabrics, additive manufacturing, and smart multifunctional materials. Professor Julia Greer obtained her Bachelor of Science degree in Chemical Engineering with a minor in Advanced Music Performance from MIT in 1997 and a PhD in Material Science from Stanford University. She worked at Intel Corporation between 2000 and 2003 and was a postdoc at Palo Alto Research Center in California from 2005 to 7. She joined Caltech in 2007 as an assistant professor and was promoted to full professor in 2013. Professor Julia Greer has earned many awards, such as being named a CNN 2020 visionary for her work investigating how materials behave at nanoscale. Hygge Award of the American Association for Advances in Functional Materials, and many others. She was named a Vannevar Bush Faculty Fellow by US Department of Defense. Her work was recognized among top 10 breakthrough technologies by MIT's Technology Review. Julia Grier is also a concert pianist. With this, I want to thank once again Professor Julia Grier for joining us this evening. Julia, we are very honored to have you with us. Здравствуйте и доброе утро. You are welcome to begin your talk, please.
Thank you very much. It's actually, you keep on saying evening, but for me, it's just the morning here. It's just about 9 in the morning. So yeah, so здравствуйте. Thank you very much to my host, and certainly doing this in the virtual platform has become the new normal. So we're all doing this virtually. So I started sharing screen. Let me do this one more time here for you. Can everybody see my screen?
Yeah, it's perfect.
Okay, so I'm going to put it in the presentation mode. And I'm happy to answer any questions. This is going to be a lot of information. And so once you, maybe once the talk is over, I would be happy to entertain as many questions as you have. All right, so you've been staring at this title for some time now, Materials by Design, so that probably makes a lot of sense. But when you look at the second part of the title, three-dimensional nano-architected metamaterials, you might be wondering, why do all these words belong in the same sentence? And so the reason for that is because I'm sure many of you are familiar with a situation like this. You go to the store and you buy all these things that you absolutely need. And the bags that you are using to hold all these materials that you absolutely need are just not strong enough. So of course, this is not the only problem, right? From the wine glass that shatters all too early, for the toast, to the balloons that pop too easily, to the I really meant to have 4 children situation. Of course, these are all examples of materials that are lightweight. And because they're lightweight, they're weak and easy to damage and tear. Now, in contrast, the materials that we know to be strong, that we know to trust. For example, if I weren't giving this seminar virtually, I would have probably taken one of these to come see you. So the weight of a Boeing 747 is roughly 1 million pounds. So if you do a very quick calculation, if I were to fly to Istanbul to see all of you at 5 gallons per mile at $2 a gallon, my ticket would have cost about $73,000, right? So I'm glad that you would have probably reimbursed me. So thank you for that. Of course, this is an example of a material that are strong and also expensive. And so, of course, the Dreamliner already reduced their weight by about a half, and so uses 20% less fuel. Now, that's another example here is the solar panels, right? So, of course, we all care about sustainability. We all want to install solar panels on our roofs, but these materials are specialized, and so they're heavy and expensive. So if either one of these features in this image falls off the roof, this is going to be bad news for everyone. Of course, that would shatter. Now, speaking of materials that are too heavy, whatever happened to the space elevator? Do you remember how maybe a decade ago or so, we kept on bringing up this concept of space elevator? Well, as far as I know, there still isn't one. And the reason for that is because of this very busy plot. As you can see, if we plot strength as a function of density in this kind of a log-log parameter space, what we see is these colorful domains. And what they represent is all the materials that we know how to make today. Now, what I'd like to point out is that here I chose to plot the strength, but it could be any other mechanical attribute. It could be toughness or it could be stiffness. And the picture that emerges right away is that we are very good as a society at making materials that are simultaneously strong and heavy or light and weak. What we're not so good at is making materials that are simultaneously lightweight and very mechanically resilient. Now, all of these colorful domains represent the material classes that we know how to make today. So the so-called white space or the target region, how do we get there if everything that we know how to make today is already plotted here? So the way we do it in our group is by introducing a concept of architecture in material design. So for example, if you look at the Great Pyramid of Giza, you can see this is the largest man-made stone monument. Of course, it's very strong. It stands 150 meters tall. It weighs nearly 6 million tons, so it's very heavy. Now, in contrast to the Eiffel Tower, which stands twice as tall, over 300 meters, weighs 1,000 times orders of magnitude less. And so what that tells us is that with proper architecting of your materials, you're able to attain the same mechanical resilience without using quite so much material. So we began this research with making micro lattices. What you're looking at is an entirely nickel-made micro lattice that's sitting on top of a dandelion, and you can see it's hardly perturbing it at all. Now, since when can we put a chunk of metal on a dandelion, right? So what you can see is that these materials are very, very lightweight. But to get to the simultaneous attainment of lightweight and strength, we need to go down 3 more orders of magnitude in dimensions. And all of the examples that you are seeing on my screen right now are called nano lattices or nano-architected materials, all of which were made in our group. There's an obvious level of porosity here. As you can see, they're very open. They're called cellular solids. And so because of that, they contain about 99.9% air. Because you can see these are very open architectures. Now, the less obvious level of porosity, of course, is this. many of these architectures are comprised of an interwoven network of hollow tubes. And the tubes are hollow on the inside. And so the largest dimension of the solid at any location is just the wall thickness of each of these tubes, which can be on the order of 5 or 10 nanometers. So you can imagine that this single material embodies every length scale from 5 nanometers or some nanometers to hundreds of nanometers to microns and eventually millimeters and centimeters. And because of that, it is appropriate to call these materials metamaterials because their properties can no longer be described only from the perspective of material science or only from the structural perspective. At these length scales, at the nano length scales, these properties are no longer independent of one another. Now, I demonstrated to you that these are very lightweight, but I have yet to show you why they're high strength. And so here's an example of a so-called size effect. So if we plot strength, so this is the strength normalized by the shear modulus, as a function of size for a variety of common metals. So these could be things like gold and silver and nickel and copper. And we'll look at them in their single crystalline form so that there are no grain boundaries. There might be defects, but there are no grain boundaries. What emerges is this very, very strong strengthening. Now, again, this is a log-log plot. So in a log-log plot, of course, a linear slope indicates a power law. So this is very powerful strengthening. And what that tells us is that if you take a very malleable piece of gold and reduce its dimensions to about 200 nanometers, it becomes very strong as steel. Okay, so this is the example of a size effect of smaller is stronger. Now, if you take exactly the same metals and change their atomic microstructure such that they now contain grains and grain boundaries, all of a sudden you see that this effect is reversed and smaller is now weaker. So the same metals, the same gold, the same nickel, the same platinum, this is a more modest size effect because it's not plotted in a log-log space. But nevertheless, it shows you that when you reduce the dimensions of nanocrystalline materials, even though they're chemically the same, their strength becomes lower. Now, the size effect manifests itself in other properties. For example, if you look at glass, so we know glass is to be very shatterable, but at the nanoscale, if you look at the tension of this single glass nanorod whose dimension is 150 nanometers, watch in this region where, right in here, you can very clearly see it forming a neck. Now, of course, we know that this behavior is much more typical of metals as opposed to glasses. This glass thinks that it's a metal, and you can see that it's deformed over 100% before failure, which is very unusual for glass. Now, here's the last example of what we call the size effect, and that is we are deforming a single unit cell of one of these nanolattices. This is made out of a very brittle material, titanium nitride, and you can see that the beams are bending and deflecting, and if you were to measure the tensile stress in here, it would exceed 1.7 gigapascals. Now, something that's very brittle, when it's being tensed with a stress of 1.7 GPa should be certainly not staying intact and it would be fracturing. But you can see that these beams are able to deflect not only once, but over multiple cycles without any evidence of failure. So the takeaway message here is this: sometimes materials get stronger, other times they get weaker, and it is possible to suppress brittle failure. But all of these effects emerge only at the nanoscale. So the big question that we had in our group was, how can we harness this beneficial size effect and proliferate that onto a larger scale? And so this is where this concept of architecture comes into play. So to do our experiments, of course, all of these materials are quite small. We have to utilize a special instrument. So if you look at this center part, this is just an SEM chamber, so scanning electron microscope. Now, we've equipped it with a variety of other capabilities. For example, here's a nanomechanical module that allows us to conduct mechanical experiments. Here's an electrochemical module that allows us to conduct electrochemical experiments like batteries and energy storage. Here's a cryogenic module that allows us to conduct experiments at much lower temperatures. And so these are the so-called different inquisition devices that we use. So what you see here are, for example, different grips and different compression tips that we use. The spacing here is about 200 nanometers. So we can pull on a pillar that's only 100 nanometers in diameter or below. So we can handle very small length scales, as well as the micro scale right here. So this is what you see here with this much larger indenture tip. Okay, so now that I've kinds of samples that we work with, I'd like to actually walk you through the steps of our hypothesis. So the hypothesis was, or rather the question was, can we somehow harness the beneficial effects of the nanoscale and proliferate them onto a larger scale? So what I'm about to show you is a nano architecture. This specific one is called an octet architecture. It's made out entirely of hollow tubes with alumina. So alumina is a very brittle material, of course. The wall thickness is on the order of 50 nanometers and the tubes are all hollow. So it's effectively your coffee mug with a severe case of osteoporosis. So it's very porous and it's very brittle. Now let's see what happens when we compress it. So as we compress it, of course, it's going to shatter and it's going to fail brittly. This is not something that people are surprised, right? So of course you can see this failure right away. It doesn't even try to recover. And you can see we have a little nanosymmetry in our instrument. So you can see how nothing surprising basically happened. Now let's repeat this experiment, but let's change one parameter, and that is the wall thickness. We're going to deposit this material in exactly the same way. We're going to use exactly the same architecture. So it's still an octet. And the only thing we're going to do is reduce the wall thickness by a factor of 5. So instead of 50 nanometers, they're now going to be 10 nanometers, just as brittle. And in fact, it should shatter even more easily. And let's see what happens here as we're compressing this very, very brittle alumina material. You can see it compressing, compressing, compressing. And then just as we're expecting it to fail, you can see what happens. This particular material thinks of itself as a sponge. So you can see very clearly exactly the same experiment, exactly the same architecture in two very different responses, all as a result of the wall thickness reduction. So if that doesn't convince you that there is in fact a size effect, then I should just stop this topic right now. So of course this fully recovers. So since that time, what we've learned is that this effect of recoverability and mechanical resilience prevails in a variety of different, much more complex architectures. You can see that, for example, they don't have to be periodic. So what you see here is a so-called bicontinuous or nano-labyrinthine architecture. So it's made out entirely of a curved surface. There are no beams. And so you can see that the stress state that develops, of course, is very complex. And yet every time it recovers, and you can see this happening on the right as well with the periodic architecture where the bottom part doesn't even, is not even subjected to the compression. Now, the density of these samples doesn't have to be uniform. In fact, you can prescribe trajectories of different densities and different designs into your architecture. So what you can see here is the example of two different densities, and you can see that the bottom part is fully compressed and densified before the top part even starts feeling the effects of the compression. And that is reflected in the stress strain data as well. So you can see the two different plateaus. So that teaches us that we can prescribe the different deformation paths and perhaps suppress failure in these kinds of materials as well. Now, these architectures can be complex in the sense that they can be fractal, so that each individual beam is comprised of these cells. You can see already that each of these legs is starting to kink. And just as we're expecting it to fail right at those kink locations, because they're clearly very brittle, you can see the architecture fully recover. So what that's teaching us is that the size effect is very powerful and can indeed be proliferated onto the larger scales by this concept of architecture. Now, as you can see, one common feature of all the architectures I had shown you up to this point was the presence of the so-called nodes. So there were junctions at the where the beams meet at these so-called nodes. So to avoid the nodes, what we've designed is a woven architecture. And what you can see here is effectively a rope. And so these are comprised of various strands like a braid or a spiral. And so at the nodes, we no longer have any of these junctions. And look at what's happening. We're able to push on a rope effectively. So we're able to tense it first and then to compress it. And you can see that it offers resistance in both directions. So it's effectively a rope that is both compressible and extendable simultaneously. And that hasn't really been demonstrated before. And so what you can see here, of course, is how much more strain these types of woven architectures are able to attain. Now, the question is, why does it happen? Why does it happen that these hollow architectures that are made entirely of brittle material are able to recover? Well, the answer actually lies in mechanics. So if you look at failure mechanisms in beams, what we know is that these hollow beams, the situation on the right, experience a local instability called shell buckling. And that is effectively what your soda can would do if you were to step on it. Now, it turns out that there's this critical ratio of wall thickness over the diameter of the beam. So if you just make a very simple model, and you can see this beam, and so the wall thickness is T, and then the radius is A, you can set the failure criterion, and that is that, of course, the local buckling would occur at something where the critical figure of merit is this T over A ratio, and then the yielding in this case would certainly be failure since it's a brittle material. So setting them equal to one another, for this particular material, alumina, we can come up with the critical fraction here. So this T over A critical for this material is about 0.03. So let's see what happens here. So it turns out that for the 10 nanometer wall thickness, this critical ratio of T over A is below 0.03. And so what you can see is that for each unit cell size, for each type of sample, it fully recovers. And you can see that from the data, certainly going back all the way to the zero strain. And this image after the deformation, you would never be able to tell that this is taken after the deformation because it looks exactly the same. Now, as we increase the wall thickness and get first to the critical thickness and then exceed this critical thickness, what you can see is that the deformation becomes a lot more jerky, a lot more catastrophic, and certainly the material is not able to recover after that. So what that tells us is that the answer must lie in mechanics, right? So let's see how close we got to this theoretical maximum and whether we got into this white space. So the plot that I showed earlier of strength of density, these that you saw in these oblong regions are the data that we had taken through the years. And what you can see is that we already, for example, by creating hierarchical nanolattices, we already reduced the relative density of these architectures by 2 orders of magnitude. And we certainly have ventured into the white space. And this was at the time when we started doing this work, and we and perhaps many other groups can now do a lot better in getting closer to the theoretical maximum. Right. So now the question is this: if it's all about the critical wall thickness to diameter ratio, just like we showed for the recoverability, that means that if we were to build a building where each beam had a thickness of 10 centimeters and had a radius of 3 meters, and then we constructed a giant building like this, maybe you guys have something like that in Turkey, and a big giant came and stepped on it, it should just spring right back, just like our architectures do, right? So hopefully you're all smiling, because of course that would never happen, because a building would never recover like this, right? So why not? The mechanics tells us that as long as the T over A is below this critical ratio of 0.03, we should be able to observe this recoverability, but we don't observe this recoverability in large scale, of course, right? So how does the size effect manifest itself here? So it turns out that the answer is all in defects. Of course, brittle materials all fail at flaws. And before any of the beam members in a building has a chance to recover, the material will locally fail at one of these flaws, because the probability of finding a flaw or multiple flaws of certain sizes in something that's 10 centimeters thick is 100%. So when we globally apply some kind of compression, the local stresses ahead of these flaws will always exceed the globally applied stress, and certainly the material will shatter and will break before any kind of structural instability takes place, like shell buckling. Okay, so because it's all about defects, let's talk a little bit more about them, and let's use carbon as our model material. So what we made here is a carbon, glassy carbon, so you know, a pencil lead effectively, pillar. So this particular one is on the order of 1.6 microns or so, and we're compressing it. Now, you all know what happens if you push really hard on your pencil lead. Of course, it's not compressible, and it starts shattering. And look what's happening with this pillar. It's now at a stress of 5 gigapascals. So this is a very, very high stress. You can see that as we're compressing it, it's really not enjoying itself. It's bending out of plane, of course, and then it fully recovers. So this very brittle, very strong carbon material thinks of itself as rubber. So how can that be? That is very, very unusual, right? And so what we discovered is when you look very carefully at the microstructure of this glassy carbon, you see these curved strands. And even though the structure is amorphous or glassy, what we discovered is that there are small regions of graphene-like ribbons. You can see that they're separated by a very small distance of about 3 angstroms. And so these segments of graphene, or effectively sp2 hybridized carbon, is what allows these regions to shear with respect to one another without undergoing global failure. So we collaborated with a group at Tsinghua University who was able to perform molecular dynamic simulations. And what you can see here is the representation of the microstructure that we uncovered experimentally done through atomistic simulations. And you can see that these are the curved regions here of sp2 hybridized carbon. Now, it turns out that in compression and tension, this behavior is prevalent in the sense that you can extend it up to 20% tensile strain. That is unprecedented in carbon, right? So it turns out that the answer really does lie in the presence of these regions. So these very small regions with the curved graphene segments are able to undergo localized shear transformations such that they can collectively accommodate the application of the global strain. So you can see in the simulations here, for example, at a very, at a very high strain of 60%, you can see that they're extending quite substantially prior to failure here. So that's the explanation. All right, so now that we know that these building blocks, the nanoscale building blocks, are able to behave like rubber, why don't we make these architectures out of them, right? Because then they should also spring like rubber. And what we learned is that in the case of carbon, non-hollow tubes, we always destroy the nanolattices. So even though the behavior of each individual building, here's an example where the behavior of each individual building block is recoverable. When you start constructing a nano-architected material out of it, it shatters every single time and fails brittly. And the reason for that is, of course, the presence of the defects and the presence of these junctions. And so this is what I would like to highlight here, which is the importance of defects in the importance of their role in the deformation of the material. Now, the good thing about carbon, and I'm just going to skip right now to here, is that when you plot this strength versus density white space that I keep on referring back to, is that it turns out that in the limit of higher density, we're able to approach the theoretical limit much better than we were able to do with the hollow alumina nanolattices. So here's where the nanolattices are right here. And you can see that in the case of carbon, we're much more able to get to the theoretical limit. And here, if you look at the strength versus density, here's the tension and compression compared to other carbon-based materials. So there's definitely promise here. Okay, so let's switch gears a little bit and let's look at the same micro and nano architected carbon. Instead of quasi-statically forming it fully, like I've been showing you up to this point, let's impact it at a maybe hypersonic velocity. So for that, we collaborated with a lab at MIT who developed this technique called Laser-Induced Particle Impact Test, or LIPIT. And the idea is that you have a laser pulse during which you accelerate these particles that are on the order of 10 to 40 microns in diameter, and you're able to document it and to image it as this is happening. So here are some of these carbon nanolattices. You can see that these are actually quite large compared to what we usually do. Here's a scale bar of 20 microns. So this thing is about 100 microns. And now we're going to shoot one of these projectiles at it, and then let's see what happens. So here's a movie that shows one of these projectiles as it hits. It's effectively a small bullet, right? So as it hits this material, and what we are discovering is that there are 3 different regimes. Sometimes the response is entirely elastic, so it just rebounds. The second type of response is projectile capture. And then the third type of a response is the projectile rebound. So where the projectile hits the nanolattice, but it's not elastic. There's an impression left, and then it rebounds. So it looks like there is a certain degree of impact resistance that these materials offer, which is very exciting for us. So we can plot the rebound energy as a function of impact energy. Of course, the one-to-one is what you would have. So you would always have the ideal impact mitigation. And if you compare our materials at the relative density of about 14%, you can see that this is the inelastic energy. Of course, this is the absorption energy. And then this is the rebound energy. So we're come pretty close to that. Now, this is for the relative density of 14%. So these are very, very porous. Now, as soon as we increase the density to about 23%, so it's about 1/5, right? So they're still not very dense. You can see that we get very close to the ideal impact mitigation in the sense that all the impacts are absorbed. And when we plot the specific impact energy, of course, that's normalized by the density or normalized by weight, you can see that our materials actually outperform Kevlar and many other materials that exist today, especially at the impact velocities that approach 1 kilometer per second. So we're very encouraged by these results and are hoping that maybe there will be some impact resistance and shielding that they offer. Okay, so I've been talking for some time now, and I'd like to maybe take a little break, and all of you take a little stretch and maybe stretch out and then take a breath. And let's find out what is this by design concept that I keep on bringing up? Because up to this point, I've shown you a variety of different architectures, and that they're exceptionally lightweight and that you can deform them in a variety of different ways, and that they will exhibit mechanical resilience and recoverability even under complex stress states. But how is that by design? And so the analogy I'd like to draw here is with coffee. Of course, all of us enjoy this beverage. So 20 years ago, the coffee situation was, how do I take my coffee? Seriously, very seriously, right? So people would just either drink coffee or not. Now, 10 years ago, we became a little more advanced, and now you can have the coffee either black or white, in the sense that you can either have coffee with milk or just coffee by itself, right? So only two choices. And of course now, and of course in Turkey, you people are the coffee experts, right? And now if you go to Starbucks or to any coffee shop, you know, you have this half calf, half decaf, double latte, skinny cappuccino, you know, with cinnamon, and etc. So the number of choices just in the world of coffee has exploded. And so now we have the freedom to design our own coffee, right? And so that is exactly what happened with the materials world. So as we've been working with these architectures, what we found ourselves doing is that we can explore the different chemistries and the resins that we put together when we manufacture these materials. And instead of buying the commercial resins, we can start synthesizing them ourselves. So this is the work of my former student a couple of years ago. What you can see is that this nickel ion is now captured inside of an organic outer shell. So the nickel ion is at the core, and now you have this organic shell. And when you undergo this acrylate-based reaction, where you effectively cross-link this polymer in response to the laser light, what you end up with is an architecture that I'm showing you here that contains nickel. Now, as we're looking at this architecture, it's about 10, the unit cell size here is about 10 microns, and each beam might be about 2 microns diameter. Now, this particular resin contains both the nickel and the organic material. So how do we get rid of the organic material? Because ultimately what we want, of course, is the nickel. Well, one way to do it is by burning it. So undergoing this process called pyrolysis, we can burn off the organics and end up with an entirely nickel microstructure. Now watch specifically the size of the unit cell here. And the unit cell size here, so it keeps on jumping, about 2 microns. So it shrunk from about 10 microns and 2 micron diameter to about 2 micron unit cell and 400 nanometer diameter. Now, when you look at each individual beam, you're kind of scratching your head saying, well, these are very porous. They don't look so nice. And also the question is, how nickel is this nickel? Is this really fully made out of nickel? So we did quite a bit of chemical characterization. You can see that mostly it is indeed nickel. We did some microstructural characterization using the TEM transmission electron microscope. Now you see the grain size here is on the order of 20 nanometers. So it's very nanocrystalline, and it's mostly nickel with some nickel carbide and just a little bit of nickel oxide. So now let's look at the mechanical behavior of this material. Now I'd like to point out again, it's nanocrystalline, it's nanoporous, and it's not exactly pure. So according to any metallurgist, this is a terrible material. It's a very low quality material. It has impurities, it has pores, so it should be relatively weak. It shouldn't have a good strength, right? Now, as we're compressing this material, you can see that it behaves just like any cellular solid would, but it doesn't recover. Again, something that we would expect for a metal. But here's something interesting. When we compare the specific strength, and what I mean by that is the strength normalized by density of a bunch of typical metals. So this is titanium, aluminum, and some and silver, some other alloys. For a variety of commercially available additive manufacturing methods, what we can see is how quickly the strength deteriorates as a function of the feature size. For example, most commercial techniques are able to produce 1 millimeter features very well, and you can see the strength is very high. But as you reduce it from 1 millimeter to 100 microns, just simply a factor of 10, you can see that your specific strength falls by 2 orders of magnitude. So what that tells us is that at our sizes, if we were to just extrapolate this plot, we should be somewhere over here. But when we plot the nickel, the very low quality, the so-called low quality nickel of our work, and compare its specific strength to that of other available processes, what we can see is that its strength is comparable to something that's about 500 microns in dimensions. And so what we're learning is that we don't sacrifice the strength. We don't have this rapid decrease in strength. And effectively at the nanoscale, materials become much more robust against the defects. So this is a very promising result. Now, taking this one step further and venturing into the world of metal oxides. So for example, titanium dioxide, is a very useful material for nanophotonics. And what you can see here is it's a similar process, but now we have the titanium ion. Of course, it's 4-valent, and so it's coordinated with 4 different alkyl chains here. And so as we're acrylating it and creating this cross-linked network, what we end up with is a woodpile architecture of rutile titania. And what's amazing is that we can induce a photonic band gap. So here's some simulations that show the dispersion relation for titania. And here's some real experimental data that shows this reflectance at particular wavelengths. And what we're discovering is that as we're shrinking the periodicity in these woodpile architectures from a little over a micron to a micron and below a micron, you can see that this reflectance peak shifts more and more towards the mid-IR range. And so you can see that it's possible to use these additive manufacturing processes to elicit a photonic response as well. Now, this whole acrylate-based chemistry that I showed you, it works very well, but it's a bit toxic. So the acrylic chemistry is not exactly very good for the environment. So we have been exploring other ways of creating the same or maybe different kinds of metals in oxides. And what my students came up with is the hydrogel-based synthesis. So you take a hydrogel, and of course, this is all aqueous environment, so it's all just effectively water. And what you can do is leach in and swell in various metal salts. In this case, it's zinc NO3 into this polyethylene glycol hydrogel. And then now that you've swollen in these metal ions, what we can do is subject it to heat, and through a process of calcination, we can get rid of the organics again. And what we end up with is a zinc oxide. So this time it's a functional oxide unit cell that's made entirely using water, effectively. Yet again, it's a very nanocrystalline architecture. And what's really interesting is that zinc oxide has a functionality of being piezoelectric. So you can see that, for example, here's one of those zinc oxide architectures. And when we apply mechanical load to it, it displaces. So what you see here, plot on the bottom right, it's not perturbed. Then we apply 200 nanometers of displacement, and you can see that there's a simultaneous voltage response, so that we still experience piezoelectricity even though it's nanocrystalline. Now, from metal oxides, the question was, well, if we made the metal oxides, can we further reduce them to their parent metal? And so what we're discovering is that, sure enough, so you can see this is cuprous oxide and nickel oxide. And we first convert them into these black, of course, the black is representative of the nickel oxide and the copper oxide. And then once we reduce them, they turn back into their shiny color. And so this is a hydrogel-based way to create metals. Now, these nanoarchitectures are also quite versatile in the sense that we can chemically functionalize them with different moieties. So you can see we can attach various aromatic parts, various alkyl chains, maybe some alcohols, something that's hydrophobic, something that's hydrophilic. Now, the important thing here is that we can attach an agent here called NBOC, which serves as a good protector. So with the NBOC functionality, you can protect and deprotect an architecture and then attach other things to it. For example, DNA. So what we were able to do is to attach some DNA to these architectures into a membrane, which can then bind to a variety of different chemotherapy drugs, for example. So this, in this particular case, it's doxorubicin that binds to the architecture and is able to function in blood and, for example, wick away excess medication for a chemotherapy patient. There are a few more biomedical applications. What I'm showing you here is a so-called shape memory polymer. So there are two different chain builders and a cross-linker. And the idea is that we can take a certain shape and then we can heat it up. And as we're heating it up, we would deform it into a configuration that we want. And then when we cool it down under stress and then remove the stress, it stays in this shape. So imagine that you're working with something with an umbrella or with a balloon, right? So you can collapse its shape. And only when you start heating it up, for example, like in a hot air balloon, would it go back to its original shape. And so these types of polymers remember their shapes. And so this is demonstrated in various figures here. So you can see that there's a flower whose petals open up as we compress them. You can see a various tower. So here's a tower that we compress that's coming back upon the application of heat. And so this could be very useful in the world of microstents and other biomedical applications. Okay. I'd like to finish by going a little bit into the energy storage. So many people these days are working on lithium-ion batteries. And so using this kind of an approach that I just showed you, this hydrogel-based approach, we set out to make a complex oxide. So this is lithium cobalt oxide. And it's a typical material for cathode chemistry in a variety of different batteries. And so what we fabricated is a carbon-based anode and an LCO, or lithium cobalt oxide based cathode. And so when you put them together, so here's the carbon anode, it's all fully architected. You can see its performance. Of course, you have this CV, IV performance with the characteristic cathodic and anodic, reduction peaks and oxidation peaks. You can see we can cycle at multiple, at different C rates. And so here's the discharge capacity. You can see we can cycle it over many, many different cycles. And what we learned is that these two actually combine very well together. And so ideally that we would eventually make this interdigitated battery. Apparently this work was so captivating that both journals decided to feature it on their covers. So you can see how this approach, the architected approach to battery design can produce, pave a pathway towards an all solid state battery where, for example, we won't be susceptible to all of these challenges with the electrolyte being unstable and of course the safety of the battery. Okay, so this is the last part. So for the electrochemically, so since we're on the topic of electrochemistry, we have explored this concept of electrochemically reconfigurable materials. So if you look at a tetragonal architecture, much like the architectures I've been showing up to this point, and now as you active anode material, you effectively would deposit a very thin layer of silicon. So it'd be about 100 nanometers of silicon. Now, when that happens, so you're looking at the top-down view now, as we lithiate it, so this is the lithium going into this anode. What you see is that it creates this pattern. So some people might think that this is a sinusoidal pattern. I call it, to me, they look like violins. So this is a very, I'm a musician. So to me, they look like, it looks like a very musical pattern. And so here's the top view before and after the lithiation, as well as the tilted view. And so you can start seeing these nodes, right? So you can see that the beams around the node co-rotate to create this kind of a shape. Now, I'm not showing this to impress you with a cool pattern. What I'm showing you is that it's truly a battery. And in fact, when you lithiate and delithiate, you can see that the pattern that's formed either buckles very closely together or then it unbuckles farther away from one another. You can see that when the cutoff voltage is on the order of 0.6, you can see very good behavior of specific capacity. Voltage versus specific capacity. You can see that we're cycling them at different rates. So it is a battery. It's not a great battery, but it is a battery nevertheless. But here's what's interesting about this battery is that we discovered in the process of charging it and discharging it at different rates that sometimes the nodes all co-rotate. And this is when you have this very nice architecture. And sometimes some of them co-rotate and some counter-rotate. So you can see that when they co-rotate, you create this very nice buckling pattern. But when they counter-rotate, you create the second mode buckling. And this leads to a very frustrated architecture. And I would like to point out, this is not elastic buckling. This is actually yielding. The material is yielding as the lithiation is occurring, and the lithiation front is progressing through the beams from the outer surface towards the inner part. So we collaborated with a research group at Georgia Tech that created these patterns as a function of lithiation. So you can see the color changing. So that's the amount of lithium that's going in. And of course, it's changing the composition of the sample. And so what we uncovered is that these domain boundaries of the frustrated buckling patterns seem to correlate with the lithiation rate. So when you lithiate very slowly, so here's your C/20 lithiation, it's very slow, it forms one large domain. And when you lithiate very fast, you can see that it's forming much smaller domains and more of them. So it's effectively, to us, it looks like a model treatment for the so-called icing model, where you have these ferromagnetic and anti-ferromagnetic switching behavior. So once you incorporate a coupling coefficient and start to recognize that there's a correlation between the rate parameter, which in our case is the lithiation rate, and in the case of the Monte Carlo simulations is this KT parameter, so it's the thermal contribution, we can see very similar behavior. So these images at the top are actual renditions of our SEM images, and the images on the bottom are computations. And so what we were able to show is that there's a band diagram that you can create as a function of lithiation. So when you start off with pure silicon, there are no band gaps. Of course, you have every state occupied. But once you start lithiating it, for example, here's a band gap that emerges. And then as you start lithiating it further or delithiating it further, which corresponds to a more relaxed pattern, you can see that these band gaps shift. And so that allows us to attain a variety of different deformations, for example, out of plane buckling or rotation or other degrees of freedom. And that tells us that we can actually utilize these defects to our advantage. And what I'm about to show you here is this. We pre-programmed a defect in here that you don't know about. And you're looking at the top view of this battery and we're about to lithiate it. And as we're lithiating it, you're going to see a pattern start to emerge. And so here's the pattern that's emerging here. And hopefully you can see right away that the resemblance between the pattern that's forming in the video that I'm showing you and the little logo that I'm showing you on the right. And so what that tells us is that we can actually, once we understand the behavior of the defect, we can use this to tailor in a specific file. Okay, so this brings me to the end of my talk. And I guess the question here is like, so what? You know, you showed us a variety of different architectures. You showed us some pretty pictures, but what does all this mean? And I'd like to leave you with the following message. If you're clever about three very important aspects of material creation, one of them, of course, is the specific architecture that you're using to develop your new material. Does it need to be periodic? Does it not need to be periodic? What kind of underlying constituent solid you're using, and what functionality are you hoping to elicit? That plays a tremendous role in governing how your material will behave, and especially affects its density and weight. The second part is the nano size effect. How does your specific material respond to the nanometer length scale? Does it become less brittle? Does it become stronger or weaker, or maybe it's not affected at all? So it's very important to understand the various aspects of the size effect when you develop new materials. And then of course, the third aspect is the atomic level microstructure. Is your material crystalline or amorphous? Is it single crystalline or is it nanocrystalline? And those are all very important aspects. So if you're clever about these three specific tuning knobs, so to speak, you can create entirely new material classes. And the reason why you would want to do that is so that we can start living in the world where instead of hearing aids, you can just write the cochlear bone directly in your ear. And so you would never need to wear these bulky hearing devices. Your iPhone 83 would hold its charge for 83 years without needing to be recharged. Of course, we're going to be able to build much more reliable and much more capable batteries. The balloons are no longer going to need to be using the helium, which is a precious resource actually, because vacuum is lighter than air. So as long as these materials can be made very stiff and non-porous, then we would be able to simply evacuate instead of using helium. Here, of course, these are Christmas ornaments, not very relevant for the season, but the idea is that we can prevent them from shattering, right, from using these architected materials so that you wouldn't break them or injure yourselves anymore. And then this is probably my last example. So it's getting to be late for you, so maybe you would enjoy a little bit of dessert afterwards. So what I'm showing you here is some chocolates. And our latest pursuit is chocolate nano lattices, which are 100% taste, 99.9% air, and 0.01% calories. And so with that, I'd like to thank you for listening. Here's I guess it's an outdated picture of my group. See, we're all not wearing masks. This is 2 years ago now, fall of 2019. Just to show you that we're actually a fun group and we do have a lot of fun together, even pre-COVID, and now finally we're all vaccinated, starting to come out of it, and all the wonderful agencies that have supported our work. And at this point, just thank you very much for staying up late and for listening, and I'd be happy to take any questions.
Thank you very much for this very, very exciting and intriguing talk, as well as a comprehensive talk. So please ask questions. You can write questions, send us through the chat button, or you can use microphone if needed. Can I ask the first question from me?
Absolutely.
Can you please elaborate? All these results, of course, are very exciting and innovative. So can you please elaborate a little bit on the present or future applications in the industry?
Yeah, well, like I showed you, for example, in the battery world, maybe right here. So I can see using this kind of additive manufacturing, especially hydrogel-based manufacturing, to create intricate geometries of these, and for example, battery electrodes, right? Or any kind of a shape that requires sophisticated shape, like tungsten, for example, is a very hard metal to work with, right? So this kind of additive manufacturing allows to manufacture parts out of tungsten, for example, right? With very intricate shapes to begin with. And so it allows the creation of just what you need. So there's not any process where you start with a large bulk precursor and then you carefully out what you need. Instead, you make what you need. So it's a lot more wasteless. It's a lot less wasteful of a process compared to commercial processes today. And it's very capable of producing specifically what you need. So I showed you some applications in nanophotonics. I showed you some applications in creating metals. I showed you some examples in the energy storage and biomedical applications, for example, creating stents. So there are many technologies that require miniaturization of devices, for example, in biomedical industry, for example, making a stent for your eye, right? Or something very, very small. So this kind of additive manufacturing of shape memory polymers, for example, would allow you to create something that's very intricate and biocompatible that can be inserted directly into your skin or into a very small vein. So we see a tremendous potential in developing this kind of additive manufacturing approaches to a variety of different applications where miniaturization and shape integrity are very important, as well as the payload. So sending anything up into space or up in the air, where of course these are made quite lightweight at the same functionality. So that's how I would answer this question.
Thank you. Thank you. We have received a question from Göre. Thank you for this great talk. How often do you use computational techniques in your research? And if you do, how useful do you think it is?
We use a variety of computational techniques. So I think I showed some molecular dynamics simulations that were right here, right? So for anything where we're trying to understand the nanometer scale fundamental behavior of the materials, we very often resort to molecular dynamics. So we do quite a bit of atomistic simulations. At the larger scale, what we do quite a bit is computations that are continuum-based. And maybe let me see if I'm showing you here. There's some continuum-based computations that we have utilized in our work, which of course predict things like the influence of the nodes on the geometry, right? Or any kind of, or like this, I think I showed here. Yeah, so here's a computational technique, right? So this is all continuum-based, and this is anything from FEM type modeling to the sophisticated models where we collaborate with other groups who develop theory to Monte Carlo simulations. So we most certainly use quite a bit of computational tools, but we don't develop them. So we either do it through collaboration or through other means. Sorry, did I answer the question?
Yeah.
Oh, okay.
Thank you.
No problem.
Another question says that, what is the most challenging path of this materials design, manufacturing, testing, modeling, simulation, or other? What is the most challenging step?
You know, it very much depends on the type of material that and the functionality that you are working with. So it was very challenging to develop all of these additive manufacturing processes. So for example, this, where's my little hydrogel based? This process was pretty hard to develop. This, we didn't know. So basically developing the new resins has proven to be pretty challenging because we didn't know if the chemistry was going aqueous photoresins while swelling in the different metal ions, if it was actually going to work. And then we didn't know about the process of calcination, if this was going to be possible, right? So creating these kinds of processes is always very challenging because we don't know what to expect. So the processing step is very much challenging. And this shape memory response was very hard as well. So I would say probably the synthesis to get to these 3D architectures is probably the most challenging step, just because it's such an unexplored parameter space that you never really know if it's going to work. And then once you've made the architecture, testing it and manipulating has proven to be much simpler than that first initial synthesis step.
Thank you very much.
Of
More
course.
question, please. So, we have one question again. Thank you for this great presentation. Have you ever tried to manufacture lighter than air designs? Lighter than air.
Lighter than air. Okay, yeah. I don't know about lighter than air, but these guys are all lighter than water. And actually some of these are 99.9% air. So I don't think it's possible to make lighter than air, but we've certainly gotten pretty close. So a lot of these architectures that you see here are pretty lightweight.
So do you use machine learning techniques in your studies?
You know, I know it's a really hot topic. We should, and I think the whole community is very interested in that. We haven't really incorporated them too much yet. There's still quite a bit of learning to do in the deterministic way, but we probably will at some point to understand. We're much more interested in the effect of defects. And of course, the defects would lend themselves to machine learning in the sense of how much does each type of defect make a difference, right? So for example, in these kinds of architectures, if you take out one bar, it probably wouldn't affect the behavior of the material. Well, what if you take out 2 bars? What if you take out 3 bars or multiple bars? At what point does it start affecting the material behavior? And then can you incorporate that kind of defect tracking into the in situ process as you're making these architectures would be a big question. And so that's what we, this is where the machine learning could probably really help. So, yeah, so we haven't actively started yet, but we are thinking about it.
Thank you.
Of course.
Another question sent us through YouTube chat. which says, how large have you been able to make these nanostructures before they start to degrade and do not have the same strength compared to nanoscale?
Sorry, how much do they last?
Yeah, how large have you been able to make these nanostructures before they start to degrade and do not have the same strength compared to the nanoscale? Personally, I did not.
It depends. It depends on the material, of course, right? So it depends whether it's a ceramic or a metal or carbon. Some of them, like the carbon materials, for example, are very, very stable. But polymer materials are really not, right? And so they start to degrade right away because of humidity and moisture absorption. So it's very much material specific. It's not so much nano specific. The nano part actually comes in through, I guess there's a lot of surface area that's exposed. And so if you're making a battery relevant material, of course, you have to keep it in the glove box. And they would be susceptible to moisture as well, right? So as you're increasing the surface area to volume ratio, this is where the stability would come or the degradation would come into play. So yeah, I would say that it's a lot more of a function of the material type and a lot less a function of the architecture. But yeah, probably by exposing a lot of surface area.
Thank you. More questions, please. So it seems that there's no more questions. So Julia, if you don't mind, we can perhaps stop here. Thanking you again for joining us.
I was going to say, you have been such a delight. Let me go back to Zoom. You've been such a delightful audience. I would be happy to, there we go, stop share. I would be happy to answer questions via email if you or your colleagues would like to send some my way. I have to take my son to school now. He's getting to be pretty antsy at this point. So thank you very much for inviting me. Thank you for the kind introduction. I hope to visit you sometime in real life. Maybe, and yeah.
Yeah, sure. Thank you very much. We appreciate very much.
Thank you, and have a wonderful evening. I hope that you have a few things to ponder now.
So you have two wonderful day.
Thank you. All right, take care. Thanks a lot.
Thank you.